Welcome to radar system course. So we see here modified radar equation. So how that radar equation is modified here with respect to all other terms. So that we started here. So now for that purpose we need supposed to know that what is the radar equation. So earlier we have discussed a radar range. So that is about a R max. Okay, so that will be the maximum radar range with respect to what will be the power density that is from the transmitting antenna. Then what will be the gain of a transmitting antenna, then effective aperture area of a transmitting antenna, then your cross section, radar cross section, that is sigma, and here we have a term a 4 pi twice of S minimum. Okay, that S minimum is nothing but what? A minimum detectable signal. Okay, so this one is about a minimum detectable signal. Now we will see here. So what will be the minimum signal required? Okay, so for that minimum signal, so we supposed to know that what will be the noise at a receiver. So generally we say that your signal is transmitting to the object and then it will be reflected back to the your transmitter and then it will be received or it will be detected. That is about a echo signal. What will be the minimum level of that echo signal that is to be detected here. So for that purpose, we again need to know about that at a receiver, what are the various components present in a radar block diagram. So what are those various components present in the radar block? We have the mixer, then a IF, okay, then a detector, and then a video amplifier. So now all these components belongs to the envelope detector. So means whichever the signal received by the receiver, it has some particular threshold value. Okay, and above that threshold value, if it is detected, then we supposed to consider that is about your that is the acceptable signal. If that signal is below the threshold value, so then we can say that that is belongs to the noise. So then we will talk about that what will be the signal to noise ratio here. So that will tell you about that what will be the noise present in the receiver or what will be the noise present or a noise came from the object or any spurious signal. Okay, so likewise, so that we need to be discussed here. So for that purpose, so we supposed to know that what are the various losses. If we consider that we have a transmitter and receiver section, okay, so in that case, we supposed to say that we have the antenna here, and then we supposed to consider that there is an object, and from that object we supposed to receive the signal. So now this is about your transmitting signal. From this object, we will receive the signal. Okay, so we'll discuss that object is moving or radar is moving. That part is later. So that is about a Doppler shift. So there will be changes in the frequency of your received signal or echo signal. Okay, so that is about a Doppler effect. So that we will see later. First of all, we just consider that echo signal received from the object to the receiver. So then what will be the minimum acceptable signal? Okay, the minimum acceptable signal by the radar. Okay, so that minimum acceptable signal we supposed to define some particular threshold value, and then for the given particular threshold value, so detection of a signal is to be carried out within a particular range of a threshold value, and then that signal is to be detected. So we should know that if that signal, if it is beyond the threshold value, okay, if it is above the threshold value, okay, so generally what we can say that we are transmitting the train of a pulses. That is about a train of a square pulses we are transmitting. But we are receiving that echo signal. It is not a square shape pulse. we are receiving some noise here. Okay, likewise. So we are receiving some noise here along with whatever our signal. Okay, if supposed to be this noise is above the that particular level, threshold level, so then that is to be considered as a false alarm to be detected by the device. So that's why we're supposed to define some threshold value. And above this particular threshold value, if your signal is there, then it is to be detected there. Okay, so now this one is about a threshold now. So above this threshold, if supposed to be signal, now this signal is detected likewise. So if the level of the signal, received level of the signal is below the threshold level, so then that signal will not be detected there. Sometimes, if supposed to be there is a noise, so in that case, that noise will be greater than this particular threshold value. Then a radar will detect that noise as a signal. That is nothing but a false alarm. Okay, so that is nothing but a false alarm, means false detection of a pulse. There is nothing, or spirits or any jamming signal reach to the radar, but it is not indicating that object is there. But we are getting some signal that is more than that threshold value, so then that is nothing but a false alarm for the radar there, or a false pulse detected by the radar. So that's why we need to know about that. What is the probability of a false alarm detected by the radar there? So for that purpose, we supposed to find out what will be the noise in the given system. Okay, or how this device or how your receiver will detect the signal with a specific level. Okay, that is to be considered here. So in general, what we are saying, if supposed to be there is spurious signal from the any other object, okay, generally in military applications and all, in a radar, so what happens, the some spurious signals are there or jamming signal is to be sent to the device there, okay, from the other part, that is about a counterparts, okay, likewise. But if you take a device here, radar, so in that case, we supposed to say that this echo is received by the receiver. So then what will be the level of that particular echo signal? That is to be find out here. That is to be detected. So for that purpose, there is a filter. Okay, IF filter and a match IF and a match filter is there in your radar block diagram. And that match filter will find out what will be the level of the signal there. So generally, it is to be detecting the given signal. But we are expecting the square, we are sending the rectangular pulses. Okay, we are sending the rectangular pulses. We are supposed to expect the rectangular pulses at the receiver, but we are not getting the rectangular pulses at receiver. We are getting somehow a pulse type, pulse shape, or somehow triangular shape of a pulses we are receiving. Okay, so likewise, so this way we are not getting exactly a rectangular pulses. Then, so how this occur? Why these particular pulses, or why this particular signal we are receiving at the detector there? Because this signal, okay, we have pulse is there, so it has some particular noise is there, and that noise is occur not from the echo signal or not from the externally, because we have a noise filter earlier case, and after that we supposed to use a IF and then match filter there, and that signal is passing, that IF signal is passing through this. Okay, so now this noise is occur at the receiver. At the receiver means what? Generally, we say that a receiver detecting the signal. Okay, receiver detecting the signal, and then what happened at the receiver? So based on that reception of the signal, so electron hole combination takes place and current is generated. Okay, now because of that particular process of a electron and hole combination and that current pulse generation. Okay, so what happened here? So we are that get that device fluctuation occur in that particular device, and due to that electron and hole process takes place, that will get heated. So that's why we are getting the a signal, and that signal having the noise, and that noise is supposed to be called as a Johnson noise. Okay, because of that a temperature. A general process at a receiver means we are converting that a electromagnetic signal to the electrical signal. So in that particular conversion or at the receiver, so noise generated. So what will be the noise in the given particular signal? That's why we say that there is some minimum detectable signal. Okay, there is some minimum detectable signal. There is some level of the minimum detectable. So what will be the minimum detectable signal level is there? Okay, so that minimum detectable signal level can be obtained through the that applying the threshold, and that particular minimum signal is to be received so that a noise can be removed from the a signal. So there is some limitations, or there is some what you can say the a limiter we supposed to use at a receiver, and then that that will define some level, and according to that that signal is to be received. Now we say that echo signal is received. So that echo signal is supposed to be that echo signal is a weak one. Okay. So how much will be the weaker signal level? Okay, because the distance between the object and your radar will be a far. So in that case, the echo signal sometimes will not be reached to the receiver then. Okay, because of the far object is far there. And we say that earlier that echo signal is to be received between the pulse repetition interval. Okay. So what is the pulse repetition interval? Means what we send a pulse here, one pulse, and after okay, there is some gap, and then we sending a second pulse. So in between this, that echo signal is to be received. So that is about a pulse repetition interval that we say. So within a particular period of a time, we supposed to receive the signal from the object. Okay, so that's why we can say that what will be the weak signal to be detected by the receiver. So that's why we say here the minimum detectable signal received or read by the given particular a device there. Now, for that particular purpose, so we supposed to define some particular threshold we say, and then above at a particular given particular threshold, we supposed to find out the that minimum detectable signal level. And this particular portion we supposed to receive by the radar. So that is just we say that a radar receiver here we are getting this particular train of a pulses at because this one is about our transmitter section and this one is about your receiver pulses, and we supposed to get this type of a pulses here. So now, so what will be the a noise present in the given particular device there? So as we say that we consider that for a given particular signal level, so what will be the signal to noise ratio? Okay, signal to noise ratio, and based on that particular signal to noise ratio, that how that noise added in the particular device. Okay, so that is to be obtained here. So we consider that earlier case in a block diagram that IF, then a matched filter. So now that matched filter rule is about what it it is to be IF amplifier. So it is to be that block is to be amplify the level of the signal. Okay, so in that case it will increase the level of the noise also. It will increase the level of the signal. Okay, so then for a given particular distance, so what will be the minimum detectable signal that is to be we find out there. Okay, that is about our role. So then how that noise come here? Okay, in a given particular system. So that noise is because of what? Because we supposed to get the echo signal, okay, at the receiver there, and that noise is generated because of that thermal agitation takes place, or we can say that while we say that conduction of electrons. Okay, so because of that increasing the okay because of that increasing the temperature. Okay, so that's why we can say that thermal agitation. So we will get that a more number of electrons. Likewise. Okay, so that's why that is about a process. So that means conversion of that whatever the signal to the expected electrical signal. Okay, or we can say that in a device itself at a receiver, when we are processing a signal there that is received by the antenna. So in that case, there will be a noise generated, and that particular noise generated that will affect the current there. Okay, that will affect the current there at the receiver input state. So that's why that particular noise is called as a thermal noise or a Johnson's noise. And that noise is directly proportional to the bandwidth and what will be the absolute temperature of the device there. So we find out what will be the a noise value. Then we will modify this equation. So this is about a minimum detectable signal. Then we need to consider that minimum detectable signal with respect to a signal to noise ratio, and then we will modify this particular equation here. So to modify this equation, so what will be the available thermal power noise? Okay, so we can say that we need to find out available thermal noise power. Generally, we say that it is nothing but what a k, t, and a that will be the word a noise bandwidth. Bn is nothing but what a bandwidth generated at a receiver there. Okay, at a receiver, and then t is nothing but what that is about a temperature, and that k is nothing but a Boltzmann constant, and that Boltzmann constant that k is equal to what 1.38 into 10 to the power minus 23 here. Okay, minus 23. So that is about a joule per degree. Okay, so that is about a Boltzmann constant. You just remember that k value. So now that bandwidth is nothing but the restricted to the receiver there. So generally we supposed to use a super heterodyne receiver. So then this bandwidth is nothing but to be considered as a at a for a super heterodyne receiver. Okay. So and that n factor is supposed to be the noise bandwidth. Okay, B is nothing but the bandwidth, but n is one factor we supposed to consider here that is for the noise here. So then what will be the a noise bandwidth? So noise bandwidth is nothing but the response of the whatever the IF here that we are using. Okay. So in block diagram we have the IF amplifier. So IF amplifier, what will be the response of a IF amplifier? So generally we say that a bandwidth is nothing but what a from the initial point to the final point. Okay, so generally we consider. But in the case of a IF amplifier, we supposed to find out that where we are getting the maximum response, where we are getting the maximum response. Generally, B is nothing but what F1 minus F2. Okay, or some people are writing F2 minus F2. But in the case of IF amplifier, so we are getting some particular response. Okay, so likewise, we are supposed to consider some particular response. So what will be the maximum value for the given response and minimum or a 3 dB point here? Okay, or we can say that a half power point. And at that particular point, so what will be the F2? Okay, so what will be the F2 and Fn here? So that is nothing but the difference between the two 3 dB point is nothing but the half power bandwidth. So in that case, we are supposed to consider a IF amplifier, and for the given IF amplifier, what will be the response? Okay, what will be the response curve? And that response curve will provide you what will be the a bandwidth. Okay, so generally we say that for the given particular response, okay, that response is with respect to the what you can say a function of a frequency there. So I suppose to elaborate here with respect to whatever the function, okay, h of f, okay, with respect to a frequency, and that will be changes with respect to a frequency there. So that's about a TF. So this is about your, what you can say, that a bandwidth. But and that response h of f is a response of your IF. Okay, it is nothing but a response of your IF here. Okay, that is to be considered. Then what will be the a noise figure, okay, for the given particular noise received at the receiver there. So generally that noise is considered is nothing but a thermal noise at a receiver. Okay, we are supposed to consider that a noise received at the receiver is because of that a thermal agitation of the electrons or a conduction of the electrons there, and because of that there will be a changes in the current. Okay, or what we can say that it will affect the ohmic response of your system there. Okay, so likewise now, so what will be the a thermal noise? Okay, that will provide you in terms of a, what we can say, that a noise bandwidth there. But at a receiver, so we supposed to know that what will be the power received at the receiver in presence of the noise. Okay, so in that case we supposed to find out the a noise power, okay, at the receiver, or we supposed to consider that what will be the noise figure at the receiver. That will be depending upon the a thermal noise. So in that case, a noise figure is equal to what? A noise out of a practical receiver, okay, whatever the noise there at a receiver, and with respect to what? A noise out of ideal receiver. Okay, so that is about a noise figure there, and that all the values at a standard temperature. Okay, at a room temperature we supposed to consider that is about a T0. Okay, so in that case it is nothing but what? A noise out, okay, noise out of a practical receiver with respect to that noise out of this ideal condition there, k T0 here, that is B, there will be the gain factor for the given device. That's why it is about a GAM. Okay, that is about the available gain for the given receiver. And K is Boltzmann constant. It's about a your room temperature here, or you can say that for the given particular noise temperature, for a given particular noise figure. So that is about with respect to a standard temperature value. Okay, or you can say that a room temperature there. And this one, this n out is nothing but the noise out of the a receiver there. So this one a noise figure defined in terms of the given particular factor. Now we need to relate a noise figure with respect to that what will be the a signal, okay, with input signal ratio at the receiver and a output signal ratio at the receiver there. Okay, so means given particular block we supposed to consider that what will be the S in here and what will be the S out. Okay, so what will be the signal in here and a signal out here. Okay, so that's why we supposed to write a noise figure equation with respect to the a input noise and a output noise. Okay, or a input signal and a output signal here. So we can write here the equation again here. Here is equal to a signal input here. Okay, that is a signal input and with respect to the signal output here. Okay, signal input with respect to the signal output. Now the term that is NIN, that is about the input noise and in a ideal condition. Okay, input noise in a ideal condition there. That is about a KT0B. Okay, that is about the ideal condition. And a N out is about the what will be the output here with respect to the given particular gain of a output receiver. So that is about a output here. So now this is about a noise figure. Now from this noise figure, a signal input to the receiver, okay, signal input to the receiver that can be related to the minimum detectable signal. Okay, so we consider here. So what will be the input signal? So consider that this one we just supposed to consider that yes in here is equal to what? This one we have a term. Okay, so we have the yes in by n in here and yes out by n out here. Okay, so now we can consider that a yes in is equal to a k t0 b. Okay, that is about a fn s out divided by whatever the n out here. Just right here in terms of this one. Okay, this one we are getting. So with this, we can find out that okay. So this one is about a input function. Okay, we supposed to consider, and then from this we supposed to find out that what will be the minimum detectable signal. Okay, yes minimum. So yes instead of yes in we supposed to write out here yes minimum here is equal to what? A KT0 B F and yes out by n out. That is again a minimum here. So now we can write here the S minimum is equal to what? With respect to the instead of a S minimum, I supposed to write or we supposed to rewrite the equation again with respect to what? A S by n minimum. Okay, S by n minimum. Okay, so we'll write here. Okay, so I just remove this term here. So instead of S minimum, we supposed to consider that a S minimum is nothing but what? A signal to noise ratio. Okay, with respect to the minimum there. So this one, our equation will be what? Signal to noise ratio, that will be the minimum. Okay, so this one is about your term. What we are getting here from this, we have a signal to noise ratio with respect to what? A R max. Now this one we are getting. Okay, so we can rewrite this equation here with respect to the given particular a noise term. Now our equation is revised. That is about F by N. That is about a signal to noise ratio. That is the minimum. So means what? It is nothing but what? A yes minimum we have replaced with a minimum. Okay, yes minimum is nothing but what? That this one. Yes minimum is replaced. Means what? We have replaced that yes minimum by yes minimum here. Okay, we have replaced that term yes minimum here, and we supposed to add here. Forgot to write that a term here. Okay, this one is about a. I rewrite the equation 4 pi. We have it k t0 b f n. Okay, with s by n minimum. Okay, so this one we supposed to rewrite here. So we have this. I think this one square earlier. Okay, so this is about it 1 by 4. Okay, so this one is about your equation, the R max. So this one is replaced with a signal to a noise ratio. This one will be replaced with a signal to a noise ratio. That is about a minimum there. Yes, minimum is to be replaced by the signal to noise ratio. Minimum, in that case, it is not what the output, okay, that is to be defined. Okay, so earlier case we obtained that a S minimum is equal to what? A K T0 B Fn just out by the N out, that is about a minimum. Okay, this one. So this one is nothing but what? S out, N out is nothing but S by N minimum, S by N minimum, and KT0 BF. And this is a minimum detectable signal. This one, it is to be replaced by the a signal to noise ratio. That is about a minimum detectable signal to noise ratio. That is about the output noise ratio. And that S by N, that will provide you the what will be the signal to noise ratio. Okay, signal to noise ratio independent of a bandwidth and a noise figure. It's not dependent because this one is about a separate here. If you consider that yes minimum here, then it is depending upon that bandwidth and a noise figure. And this one is about a signal to noise ratio. Generally, we are supposed to consider that we have the IF block here because we are providing the signal from the mixer, okay, to the IF, and then we have the match filter here. So we are getting the a out signal there. That is about nothing but we are getting the a signal to noise ratio at this particular block here. Okay. So now from this we consider that what will be the minimum signal we are getting. Okay, we just consider. So now what will be the probability to find out probability of a false alarm. Okay, false alarm. So that means what we can say that we are sending the train of a pulses, that is rectangular train of pulses we are sending, and we are receiving that likewise. So now in which in this particular case, so this is that it belongs to the noise. Okay, this if supposed to be we are decreasing the threshold, this comes here. If we supposed to increase the threshold, okay, so we are just getting a little. Even if we decrease it, so again another noise will come in the picture. So we supposed to find out that what will be the probability of a false detection of the pulses. Okay, or probability of a detection, false detection of the alarm. Okay, so this way we supposed to consider. Now in that case, we find out the what is the what do you mean by the envelope detector. So envelope detector means what? Envelope detected because of what? We have the mixer. Okay, so we say that we are providing the input from the mixer here. So this one is about a mixer. To what? To we have the IF amplifier. Okay, it's about your IF block. I consider that this one is about your IF amplifier here. Then after that we have a detector or a demodulator we say. Then we have a video amplifier. Okay, earlier diagram we have explained that a radar block diagram earlier. And a combination of this after video amplifier that will go to the threshold. Okay, that will go to the threshold and your signal is detected there. Okay, that's about a detection of. Now these particular three blocks are belongs to the envelope detector. Okay, these particular three blocks are belongs to the envelope detector. Means what will be the signal received? Okay, echo signal we are receiving, and then from the given particular echo signal. Okay, or we say that your device because it works for a given particular bandwidth. Okay, this IF amplifier works for a given particular bandwidth. So here we have the bandwidth of a IF. So within this particular range, then your signal detected by this IF, otherwise it will be rejected by the IF. It is nothing but what? A, a rejection filter. Generally we say that a rejection filter, or it will rejecting the pulses, or it will rejecting the echo signal that not belongs to the given particular signal, to a particular uh, transmitting. Okay, so that's why we are what we are expecting that particular signal that will be received by this IFM. Okay, so then we find out here. So what will be the probability of a false alarm, false detection of pulse? Because we say that there is a threshold. If it goes above the threshold, okay, whatever the signal detected. Now this one is about detected signal after threshold. If the signal detected that, okay, that we are saying that according to the threshold, we supposed to get the signal. Okay, so this is about our signal now. These are the noise part here. This one is about our signal. This is nothing but a noise. So now above this, so this is about your train of pulses we're supposed to consider. This to be detected. But if supposed to be, we decrease the threshold value, so this one is again detected. These are again the pulses detected. So now this one, we're supposed to find out for a given number of pulses we are sending. And apart from that number of pulses, which pulses we are receiving. Okay, apart from sending the number of pulses, suppose I am saying that 100 number of pulses I am sending. From that 100 number of pulses, how many pulses received by the receiver? Okay, so that is again we need to discuss. And then from those pulses, or okay, forget about that 100 number of pulses, we are receiving the signal or we are getting the echo signal, then receiver is detecting the echo signal. And out of that 100 number of detected signals, so how many signals will be detected false? Okay, so that is to be find out the probability of a false alarm. Means what? If the threshold is going to be okay as per the given particular, if it is the given level, but sometimes a noise is a higher now. So this is nothing but a noise. So now this is nothing but a noise part. A noise. So in that case, so what will be the? This is nothing but a false detecting signal here. Okay, so what will be the probability of a false alarm? So that's why we need to find out at the receiver side what will be the combination of a components we are using. So in that case, we are supposed to consider that receiver noise at the input to the IF filter. Okay, this one is about your IF here. So in that case, this filter, IF filter, it is IF amplifier here because it receiving the signal. If it is a noise, it is receiving the signal. It is that IF again it amplified because it is a IF amplifier. So then we need to find out a probability of finding the what will be the a noise voltage here. Okay, received by this IF filter there. So in that case, we can find out what will be the a noise voltage, that is about a probability of a noise voltage is equal to 1 by under root of a twice pi. I will explain you one by one term there. Exponential of minus b square by twice of size. Okay, now this b is nothing but what? A noise voltage. Okay, this is about v is nothing but the a noise voltage. So we need to find out. So okay, so what will be the level? Okay, what will be the level of the voltage here? Okay, what will be the level of the voltage? For example, I am supposed to consider that this one is about a threshold value now. This one is about a threshold now. So this is about our threshold now. Okay, so that's about a for a given particular envelope here. So this one is about a threshold value. Okay, and then we supposed to consider that. So what will be the level of the given envelope here? Okay, so this one we supposed to consider that it is about a level here. So we can say that SI0 by whatever the your input signal. That is about a mean square value of a noise here. And then what will be the, we need to talk about the duration of a pulse here. Okay, even if it is a, how many number of pulses we are sending, suppose 100 pulse, we supposed to expect the 100 pulses at the receiver there. Okay, and then each and every pulses have some particular duration we supposed to consider. Okay, so that's why we supposed to find out the, what will be the a false alarm time, what will be the average time here. Okay, and what will be the false alarm time means. So this is about a pulse we are expecting. So this is about a duration, because we say that a train of pulses we are sending. So in that particular train of pulses, we say that there is a pulse repetition interval. So in that case, whenever we are receiving the echo signal, so what will be the interval here? Okay, time interval. So that is to be identified. So that is identified based on the probability density function of the envelope. So what is the envelope here? So we are supposed to consider that if one particular frame of a signal that is to be received by the receiver. Okay, so that's why we can write in terms of a that envelope value instead of a voltage here. We supposed to rewrite the equation, and we supposed to find out the, what will be the probability that the envelope of the noise voltage will exceed the a threshold voltage. Okay, so that's why we supposed to find out that instead of a voltage here, we supposed to consider that a term with respect to that envelope here. So we can rewrite the term P of R here, R of psi 0, we rewrite in terms of the envelope here. And this is about a probability density function with respect to that envelope, and that is nothing but a form of a Rayleigh function. So that's why we can consider that a Rayleigh probability density function. So that's why a R term is we are supposed to be used here. Now this is about a function. Then we consider that what will be the threshold value above this and below this. So in that case, a probability, that is, we say that a threshold value Vt here, and we are expecting that a envelope here within that particular period of a time. So in that case, so within from this Vt to whatever the infinite value. Okay, I'll write directly the equation, exponential of what, minus Vt square by the twice of psi. Okay, that is about a mean square. Then from this we can find out what will be the probability of a false alarm. So that represents the probability that a noise crossing the threshold, okay, noise crossing the threshold, and that will gives us the probability of a false alarm, this particular term. Okay, this one is about it. I'll just rewrite again here. This is about a probability of a false alarm, exponential of minus. Okay, so we can consider that Vt square here by twice of psi. Okay, this one is about our term, and we consider that. So what will be the average time? So this one we see that this pulse noise. Okay, so this is about a time here. So what will be the average time that false alarm will be takes place? So we can consider that a false alarm time is equal to limit. So how many number of pulses we have? Okay, with respect to given particular false alarm will be takes place there. 1 by n, k is equal to 1 to n. That is about a tk. So k is what? We have the pulse 1. So that's why a k, another pulse, k plus 1. So likewise. So that is about a tk here. So next pulse, tk plus 1, tk plus 2. That's why. That is about what we are saying, that is a TFA. So from this a TFA, we can write a equation. Okay, we can write here a false alarm here with respect to the a bandwidth. So T of FA is equal to what? 1 by B exponential of